Hi again. As you observed in the last video, we were discussing the potential flow and different aspects of potential flow. We mentioned that there's a class of different solutions to potential flow, that we usually characterize them by their complex potential function, WZ. One class of these solutions is called corner flows that go as A times Z to the power of n. For the case of n equal to 1, as you remember from your lectures, it gives us something very simple. It's a uniform flow. WZ becomes U0 times Z, and that's a uniform flow that everywhere in the domain has exactly the constant value U0. We also saw that we can actually construct some more complex shapes and more complex geometries with our flows. For example, if you take the other analytical function, WZ being equal to a constant n divided by Z, in the lectures we discussed that will give you what we call a doublet. And if you recall, we showed that if we combine these two together, so if we construct a new WZ, which has a uniform flow part and also a doublet, and we linearly superpose these two solutions on top of each other in this manner, that U0 is outside of the parentheses. Inside parentheses we have Z plus A squared over Z. If we take this complex function and look at the flow for this complex potential function, we will see that it actually gives us a streamline that is exactly a circle with a center at the origin and a radius equal to A. And far away from this origin or the center of this circle, we will have uniform flow because this part of our function goes to 0 at Z equal to infinity. We will be only left with U0 times Z. And inside the cylinder, we don't feel really uniform flow anymore. We will have the doublet flow. But for purpose of clarity, I haven't drawn that here. It just makes the drawing more crowded. But you can clearly see that this is a perfect potential function to help us mimic the shape of the flow past the cylinder. Because far away from the object is uniform. Close to the object, at least one streamline exactly follows the profile of the cylinder. So it's a cylinder, and then it goes as two horizontal lines, one from negative infinity to here, and the other one from here to positive infinity. And the 2 points that we have, one point here at theta equal to pi, and the other point here at theta equal to 0. These 2 points, as we discussed before, are the stagnation points, because once you look at the velocity profile, which can be easily calculated knowing the complex potential function, you can separate the real and imaginary part of that, which are respectively the potential and the stream function. Take the spatial derivatives of these two scalar functions and find the velocity components. The radial component of velocity Vr in this flow becomes a U0 multiplied to 1 minus A2 over r squared. The whole thing multiplied to cosine of theta. And v theta for this flow becomes U0 again with a negative sign multiplied to 1 plus A squared over r squared. And the whole thing is also multiplied to sine of theta. And we observe that Vr and v theta indeed tell us that velocity is the radial component of velocity, Vr, is 0 everywhere on the cylinder, where r is equal to A, because this parenthesis becomes equal to 0, which is a perfect thing for us. It tells us that there is no flux going into the geometry, which is one of the conditions that in potential flow we need to satisfy, the no flux condition. But v theta, on the other hand, on the shape of the object can have non-zero values, which is again in accordance with the simple physical fact that we mentioned. In potential flows, we don't have the no-slip condition anymore. We cannot really satisfy the no-slip boundary condition because we have reduced the order of the differential equation 1 degree by ignoring the viscous terms. So we indeed have v thetas that are non-zero. There is, however, 2 points that both Vr and v theta, or in other words, the overall velocity vector, becomes equal to 0. And that happens at theta equal to 0 and pi, because sine of theta is 0. And since we are sitting on the cylinder, automatically the prefactor in the Vr expression is 0. So for these 2 points, both velocity components are 0. And that's what we know or recall as stagnation points. So theta equal to 0 or pi are the two stagnation points that we have in this flow, and they are sitting in the front and back of the object in a symmetric manner. The flow has a symmetry from top to bottom, and it has also symmetry from the front to back. And once we find in all these potential problems, potential flow problems, once we find the correct combination of complex potential functions that give us the shape of the object, the rest is just doing some mathematical manipulations and mathematical steps. We can calculate the velocity components. Once we have the velocity components, we put them in what we recall as Bernoulli equation or principle, and from that we can actually find the pressure distribution everywhere in a space. So P as a function of r and theta. And we showed actually in this specific problem, or many similar problems, we are specifically interested on a spatial place for pressure, and that's the pressure around the object or on the object. And we defined this pressure coefficient, Cp, as a function of theta on the cylinder, which is pressure on the cylinder, so where r is equal to a, that is varying around the cylinder as a function of theta is varying, P of every point on the cylinder minus P ambient divided by half of rho u0 squared. This is a dimensionless group. As you can see, on the top we have a pressure unit, and in the denominator we have also half of rho u0 squared, which is the dynamic pressure. We could calculate this, and we showed that it's indeed 1 minus 4 times sine of theta squared. So that's the expression we found for pressure distribution.